everyone, I am Stoica. I am a faculty at UC Berkeley, director of the RISELab, and I'm also executive chairman at Anyscale and also Databricks. Thank you for having me. In this talk, I will discuss the trends in computing, the challenges these trends are introducing, and how we could address these challenges. Distributed computing is not new. Almost every decade, a new category of applications when distributed. Arguably, the first distributed system was the ARPANET, the precursor of today's internet, which started in the early 1970s. ARPANET gave researchers the ability to remotely access the very few powerful mainframes computers across the country. ARPANET also led to the creation of email by Ray Tomlinson in 1971. 1980s saw the emergence of high-performance computing, or HPC for short. HPC started in 1985 with a partnership between National Science Foundation and 5 universities across the United States. This led to powerful simulators which allowed engineers and researchers to design airplanes, do weather forecasting, molecular modeling, and much more. 1990s saw the rise of the internet and the web. This led to building highly distributed systems to support popular websites visited by hundreds of millions of people. In 2000s, we saw the emergence of big data. As the internet companies were accumulating huge amount of data, they wanted to get a better understanding of their users to improve this user experience as well as their own businesses. So, as you can see, over the years, more and more workloads have become distributed. And once they become distributed, they remain distributed. Despite all this development, distributed computing is still in its infancy. Today, distributed computing is very hard. It requires you to be an expert, and thus it remains inaccessible to most developers. To compound with this challenge, today few universities offer distributed computing classes to train such experts. But we believe this will soon change. Driven by the demand, we believe distributed computing will become the norm rather than the exception. So what is different this time around? Well, 3 things: the rise of the deep learning, the end of the Moore's law, and more applications becoming AI-centric. I am going to discuss each of these trends next. First, deep learning demands are growing faster than ever. This is a famous OpenAI plot showing that over the past 8 years, the computation requirements to train the state-of-the-art models has astonishingly increased 35 times every 18 months. And this is not only true for esoteric models like learning how to play games such as Go or Dota 2, but also for models targeting practical application like language translation and image processing. And it is not only true for processing, but for memory as well. Here is a plot of the model sizes for the past 4 years. It shows that the size of the state-of-the-art models, or more precisely, the number of parameters of these models, has increased 20 times every 18 months. And if you look at the past 2 years alone, it has increased 200 times every 18 months. This is just unheard of. On the other hand, the Moore's law has ended. Indeed, as shown here in another famous plot, the performance of a single processor core used to double every 18 months. Now, it increases by just a few % over the same time period. To put things into perspective, Here we show the performance increase of a single core overlaid over the OpenAI plot. As you can see, the performance gap is enormous. In fact, even if Moore's law hadn't ended, it would still fall way short of satisfying the demands of training these models. So what about specialized hardware, you may ask? After all, we are living in the golden age of specialized processors that trade generality for performance, such as GPUs and TPUs. Well, it turns out that even those specialized processors are far from enough to fill the performance gap. Here we are overlaying the performance of NVIDIA GPUs and Google TPUs over the same OpenAI plot. As you can see, while they do provide orders of magnitude improvements over a single processor, their performance doesn't grow faster than Moore's law. As such, they still fall way short of the demands of the machine learning models. And this is true for memory as well. Over the past 4 years, the GPU memory had increased about 1.5 times every 18 months, while the model size has increased 20 times. And unlike processing, we cannot do much about memory in the way of specialization, as we still need a few transistors to store a single bit of information. Thus, to support these machine learning workloads, there is no other way than distributing these workloads. Finally, most applications are becoming AI-centric. Indeed, virtually every application today is incorporating now elements of AI, including e-commerce, financial application, manufacturing, healthcare, and many more. Furthermore, more and more of these applications are starting to integrate AI with other distributed workloads. This has not been the case so far. Traditionally, distributed workloads have been isolated. Indeed, HPC, big data, microservice applications have been using different software stacks and run on different types of clusters. However, this is changing. Not only applications are becoming AI-centric, but more and more of these applications integrate AI with other distributed workloads. AI is already overlapping with high-performance computing. Distributed training systems like Horovod are leveraging MPI, a system developed by the HPC community over the past 30 years. Similarly, some industrial reinforcement learning applications are leveraging large-scale simulations running on HPC clusters. AI and big data are strongly overlapping, as most AI applications today need huge amount of data to train sophisticated models. Finally, the microservice architectures that powers many of today's backend services are starting to integrate machine learning components, such as model serving, to improve these services. In summary, on one hand, the demands of the AI applications are growing much faster than the capabilities of a single processor or a single server. On the other hand, virtually every application is becoming AI-centric, and these applications are more and more integrating AI with other distributed workloads. As such, we believe that these trends together will soon make the distributed applications the norm rather than the exception. Despite the convergence of distributed workloads, systems used to support these different workloads are as diverse and distinct as ever. There is no single framework to support end-to-end distributed application integrating these workloads. So, what people do today? The most common solution is to stitch together existing frameworks. For example, Spark for data processing and getting insights from the data, Horovod for distributed training, Seldon for serving, and maybe Sync for business logic, implementing business logic. The challenge with the solution is that each of these frameworks has a different API, which makes development very hard. Similarly, deploying and managing multiple frameworks can be very challenging. This is exactly the challenge we set for ourselves to solve with Ray. Ray is a universal framework for distributed computing that we have developed over the past 4 years at RISELab at UC Berkeley. Instead of having to stitch together different distributed systems to support complex end-to-end applications that integrate different workloads, you can run all these workloads on top of Ray just using different libraries. As a result, Ray can provide support for all major workloads. So how does Ray do that? Well, Ray is designed around 3 key ideas. The first is generality. When it comes to computation, any imperative programming language provides 2 abstraction, functions and classes. Ray enables the developers to execute both functions and class instances remotely. This is very general, as it allows Ray to support both stateless and stateful computations. Second, Ray executes function and creates class instances asynchronously. This means that a call returns immediately before the computation actually takes place. This allows the caller to immediately launch another task, and then another one. And all these tasks will be running in parallel. Finally, Ray provides a distributed object store. This allows for efficient transfer of large objects. For example, if multiple tasks on the same node access the same object, this object can be shared among these tasks. Here are 2 examples illustrating the Ray API and how we can scale up Python programs using Ray. On the left-hand side, we have a simple program reading 2 arrays from 2 files and adding these arrays up. On the right-hand side, we have another simple program that allows a class that shows a class implementing a counter. Ray allows the developers to easily parallelize the execution of the functions and classes. To do so, first we need to add a remote decorator to the declaration of the functions and of the classes we want to execute remotely. Next, we need also to add remote when we execute these calls. This will let Ray to execute functions remotely as tasks and instantiate the classes remotely as actors. Recall that task and actors methods implement a future abstraction. That is, they return immediately a pointer to the result instead of waiting for the result to be produced. To get the results, we need to call ray.get on these futures. Finally, Ray allows the developers to specify the resources for each task and actor. In particular, the developers can specify how many CPUs, how many GPUs, and how much memory a task should be allocated when running. So let's see how this is working step by step using a simple example. Again, assume we have a distributed systems where with 2 nodes, where node 1 stores file 1 and node 2 stores file 2 respectively. The first function here the first function call submit the task to read file 1. Since file 1 is on node 1, we assume the task is scheduled to node 1. Recall that the execution is asynchronous and it returns immediately the future or the reference to the task result, not the result itself. This allows us to immediately execute the next function call that submits a task to read file 2. Again, this function returns immediately the future to the task result. So now we can submit another task that adds the results produced by the first 2 tasks by passing as arguments the future of these 2 tasks. Note that at this point, none of the tasks might have been scheduled, let alone executed. To get the result, we need to call ray.get on the results future. This is a blocking call that waits for the entire computation graph that produces the result to finish the execution. When done, it returns the sum of the two arrays to the program. The important point to note here is that submitting the task asynchronously enabled Ray to exploit the parallelism, which in this case meant executing the two tasks, reading file 1 and file 2 in parallel. While Ray is very general, its API is rather low level. To make Ray a truly universal compute engine, we need to make it easier to run any workload on top of Ray. The way to do that is to provide libraries exposing a higher level API that is easy to use. Fortunately, Ray has already a rapidly growing ecosystem of libraries. Ray can run on a variety of platforms, including Alluxio, and already comes with a few native libraries. First, it comes with RISELab, the most popular scalable reinforcement learning library, which supports both PyTorch and TensorFlow, and has arguably the largest number of reinforcement learning algorithms. Tune is a popular high-parameter search algorithm. In fact, Max Pamperia, the creator of HyperOpt, another hyperparameter search library, believes that in long term, Tune is in the best position to dominate. Finally, just recently, we launched RISELab, a model serving libraries. It has already generated a lot of interest, though still it has a long way to go. While we are happy with the Ray native libraries, we are even more excited about the third-party libraries that are starting to be ported or being integrated with Ray. So let me say a few words about these third-party libraries. Horovod is the most popular distributed training library and is now integrating with Ray. The same is also the case for Optune and HyperOpt, two popular hyperparameter search libraries. Hugging Face and Spacey are two of the most popular natural language libraries, and now they are using Ray to scale up. In addition, major machine learning cloud platforms such as Amazon SageMaker, Azure Machine Learning, and Model Arts from Huawei are embedding Ray in its libraries. Recently, Dask, a popular Python distributed framework with a great data frame library, has been also ported on top of Ray. Ray allowed Dask to achieve better stability and reliability. Ray also has an online integration with white biases, a popular experiment tracking platform for machine learning applications. Analytics Zoo, Intel's data analytics and AI platform, integrates Ray side by side with Spark and TensorFlow, and it's already used in a variety of cutting-edge use cases, including streaming machine learning application deployed by Burger King and BMW. And there are many other libraries I will not have time to go over during this talk. I hope that you are now at least intrigued by Ray and its ecosystem, and you will likely give it a try. We cannot wait to see what exciting application you will be creating using Ray and its libraries. Next, let me tell you a bit of Ray adoption. So this plot shows the number of GitHub stars over the years for 4 very popular open source projects: Apache Spark, Apache Kafka, MLflow, and Ray. Like you can see from this plot, Ray's growth is very fast. It actually tracks very closely the growth of Apache Spark, another open source project we developed at Berkeley many years back. The number of contributors grows also very fast. It approaches 400 contributors, and it more than doubled since last year. And it's not only that we have many contributors. Many of these contributors are making very meaningful contributions, like providing Java API besides the default Python API, refactoring some of the main components in the Ray architectures, providing Azure support, and many more. In summary, Ray is a universal framework for building general purpose distributed applications, and it has already a comprehensive ecosystem of scalable libraries. So we hope that if the future of computing is distributed, then Ray will be the future of distributed computing. And some of you will give it a try. Thank you.